I'm Swedish, but no one's perfect, and this is maybe the fifth time I'm in the Ukraine and Kiev, which is literally my favorite destination in all the part that I cover. Great food, great people, amazing sights, and this event it's really world class. I mean, the amount of people we get in, the quality of the arrangements, it's really great. So I'm going to talk to you about StealthWatch, or how to use the existing network that you have as an enforcer and as a sensor. So we're really talking about taking security into the network. Traditionally, when we talk about network security, we still talk about appliances. We still talk about perimeter security. Let's talk about real network security, security in the switches, in the routers, in the firewalls, using the network fabric as your security sensor to detect threats, policy violations, do forensics, but more importantly, how can we use those switches, routers, wireless LAN controllers, all the stuff we already have to block threats? When we see something bad coming from somewhere, how can we get that switch port to throw that user off? Those are things that we're going to cover. So the agenda looks something like this. We're first going to start to talk about StealthWatch. What is it? That's normally my key challenge when I speak to a customer. This is not an IPS. This is not a SIEM tool. It's not a firewall. It's not antivirus. It is something that you most likely have not been thinking about before. It will solve challenges that you knew you had, but you didn't expect that you could solve. So if you come out of this session today and have a good understanding what StealthWatch is and how we can use StealthWatch to use your network as a sensor grid and an enforcement point, then I'm very happy with my job. So we'll see when you fill out the reviews. We're going to talk about how you can use the existing parts of your network using NBAR, syslog, NetFlow, all these kind of functions we already have in the network fabric. We're going to talk a little bit about network performance monitoring. I'm not going to go into depth, but one of the main use cases I see for network people, I'm sure there's a lot of network people here, not only security. What happens inside your organization when something goes wrong? They blame the network team, right? Network is down. Something's wrong. Call the network guys. And then we run around trying to do PCAP, we do Wireshark. Oh, what's going on? What's going on? 2 hours later, it just works. But it was the network team's fault, right? So what if I can use the network as a sensor and say, you know what? It's not a network problem. The round trip time of the network is 4 milliseconds. That server over there has a response time of 4,000 milliseconds. Why not go and speak to application? Or maybe go and speak to the guys who runs that server, which hasn't got enough memory, right? It is a security product, but the network team, they love this. They really, really do. Just with one click, okay, this is the user, this is the flow from the client to the server. Network, okay, it moves across all the interfaces. The round trip time is fine, no congestion. But that server over there, that's, go and speak to those guys. We're going to talk about integrating using ICE, Cisco Identity Services Engine. This is a natural next step. ICE tells you who is the user, what's the device type, what's the location, what's connected at the edge. That's what ICE tells us. That's a great first step. That's a security guard that checks your ID before you enter the building. But once we're giving you access using ICE, what about if you're someone like Edward Snowden? Or just someone who managed to fake your way into the building? We check your access, network access control, it's very important. But once you're inside, we use the network to establish, identify, and mitigate bad behavior as well. ICE will tell you what's connected, will tell you what are they doing once they're connected, and is it malicious. We finish up with an architecture and summary. I'm going to do a very, very short demo. Normally I speak for a couple of hours about this. This is going to be 1 short hour. So I'll be around for a couple of hours if you want to talk more in depth. Right, so let's talk a little bit about Cisco and StealthWatch. StealthWatch is a product that was sold by a company called Lancope. I've been with Cisco for 10 years. 18 months ago, 2 years ago now, I did a big mistake. I quit Cisco. I'm like, enough is enough. I've done this for 8 years. I'm going to do something else. I just have to. And I joined Lancope for 18 months. And Lancope was acquired by Cisco. So I'm back doing the same thing. I'm very happy about that. But the story is that Lancope as a company sold the product StealthWatch into the Cisco Security Operations Center, the SOC. The SOC went to the business and said, this is one of our most important and useful tools. Can you please put this on price list and OEM it? Sell it under the Cisco brand. Then they call it cyber threat defense, then they call it network as a sensor, network as an enforcer, it's all the same thing. And we went from doing like $5 million to $100 million in kind of 2 years. So that was probably a good move. This is the fastest growing area for StealthWatch in the world, the region that I have the pleasure of running. 900% in Q1, and Q2 is looking something similar. And we were the strongest performing region outside the States before. So this seems to resonate in the region fairly well. So I'm back, and Lancope was acquired. So the main purpose, really, and the main challenge that we solve, that many of us don't think about from a security perspective, is visibility. Because we invest here. We invest in security in two places traditionally. The endpoints, we put agents and stuff to try to secure them. And then from a network perspective, we put in appliances at perimeters. We guard the borders. We guard the crown jewels that sit in the data center to make sure we don't get bad traffic flowing through that perimeter. And we guard against the internet. That's kind of what we've been doing for a very long time. And that's challenging. You know, it's not easy to secure an endpoint. It's not easy to secure the perimeter. That's where most of the investment goes in. The problem, however, when I sit down and talk to a customer, it's like, how much do you see of the traffic from a security perspective? How much traffic flows through these devices? A lot of the time, 20, 30, maybe 40%. Because most of the traffic is actually going somewhere else. It's east-west in the data center. It's in the branches. It's in the LAN segments. Stuff that not always, or even most of the time, communicate over that security perimeter that you defined. So what if we can use the routers, switches, firewalls, wireless LAN controllers, UCS chassis, any connect agents, the stuff that you already have, using standards that's already implemented and features you already paid for, to go from 30, 40% to very close to 100% visibility. So that's the first step. Just get the visibility, get the data in, and then we do big data analytics to understand exactly what's going on. Has someone been speaking about OpenDNS before here during these sessions? No? A little bit? Okay. So OpenDNS does big data analytics on DNS, which is metadata. What goes on in the internet. A good way to think about StealthWatch, we do the same thing, but inside your network. We do anomaly detection, we use behavioral algorithms, big data crunching, but looking at inside what's normal for your network, what's normal for your users. So kind of the same kind of way of thinking about it. These are the 4 main use cases for StealthWatch. The first one is, once you start engaging using NetFlow and getting visibility from switches and routers and other network equipment, instead of just visibility from the perimeter perspective, you see a lot more. You get to a point where you say, once you've had a breach, I could actually see every IP to IP connectivity. Many of my customers, they mandate NetFlow for every switch, every router, every VPN concentrator, every wireless in the data center. So they can confidently say, as soon as an IP address shows up, I see every IP to IP communication everywhere. So that's kind of the first piece. The second piece is when you get all the telemetry data and information about all IP to IP communication, we can actually start looking at policies. A great example, and a very simple one, is looking at a military-grade network. Military-grade networks do not connect to the internet. Fine. How do we know? How do you know that that network, which you're 100% sure does not, the policy says, this is my internal IP range, it doesn't connect to the outside? It's very hard, right? But if you turn on NetFlow, you can just create a very simple policy saying, this is my internal IP range. If anyone on my internal IP range communicates to anything on the external IP range, in other words, anything else, give me an alert. Or it can be surveillance cameras. Surveillance cameras should only communicate to the surveillance camera servers. Everyone here maybe heard about the DNS attack? Sorry, question? No, okay, yeah, you heard about it. Okay, great. Yeah, so DNS was the biggest DDoS attack in the world. It happened a month ago. And the interesting thing about this terabits of traffic syncing DNS, which means Twitter was down, Facebook was down, Google was down, everything was down because no one could process DNS. It wasn't executed by PCs and Macs, it was actually surveillance cameras. So the policy for those kind of things, how they should operate inside the networks, are very simple for us to define. So if you look at things like a surveillance camera, just write a policy, say, these are my surveillance cameras, this is the IP range. They should only communicate with the surveillance camera server. If anyone breaches any of these and they start doing other things, I want an alert. Other examples of policies could be, I don't want any telnets in my infrastructure. I have 2 DNS servers. I don't want any other servers serving DNS inside my infrastructure. I don't want any rogue DHCP servers in my infrastructure. I have certain secure applications, banking applications, or other sensitive applications that should only be accessed by certain terminals over certain ports and protocols. It's very hard to know if these policies are actually in place. Think about firewalls. How do we know we don't have telnets anywhere through a firewall? We just hope that the policies are in place. But when we get this telemetry data from every point in the network to one single place, it's very simple. If we see any outside to inside communication of a telnet, give me an alert, and we'll tell you who is the user, what's the device type, when it happened. The third thing that we do, we gather all this data from every single switch, every single router, and we see every IP to IP communication. Then we look at what's normal behavior. So we take the surveillance camera example again. We create a group for surveillance cameras. We look at what's normal behavior for them. We do a baseline over a week, 2 weeks, a month, rolling over 3 months constantly. And then the algorithms, we have around 150 patented algorithms. So when we see a surveillance camera doing something else, starting to scan, trying to touch other devices, trying to connect to the internet, the algorithms will see this is not normal behavior. These surveillance cameras have never done this before. This individual surveillance camera is doing something that no other surveillance cameras are doing. This can be worms, DDoS attacks, it could be data exfiltration, data hoarding. We have 150 algorithms that just using common sense, what's normal behavior, and it will alert you and you'll be able to take action based on those alerts. The last piece, and that's something that a lot of customers, including Cisco internally, has as a major use case, is just being able to do forensics. So with large organizations, or even small ones with a couple of 100 employees, it gets tricky once you see you've had a breach, you see you had an indication of compromise, but how do I know exactly what happened? I can't save all data in big storage array and do packet capture. That gets very expensive, and we can't really scale. But using NetFlow and metadata, we can save literally every IP to IP communication in your network for years on a couple of terabytes of storage. So a typical use case is your source fire devices fire, and they say this device seems to be infected. You dive then into StealthWatch, and I say I want to see every single thing this device that my IPS tells me is infected has been doing over the last 48 hours. 3 months, 6 months, 1 year, to see how did this get infected, has it spread somewhere else, what are the consequences of this, to get the same kind of visibility internally on your network as you do as it traverses the perimeter where we have all our deep packet inspection devices. Right, so let's take this a little bit lower down and see how does these main features translate into a solution. The first thing you need to do, you need to turn on Flow on your devices. Flow is an accounting format. It was invented for network performance monitoring. Once you turn Flow on, NetFlow, There's an open standard called IPFix, which is implemented by many other vendors. We can work with that as well. Once you turn it on, the devices that we see here on the left, they start reporting information about the traffic they see. It's kind of like a phone statement or a phone bill, but for network traffic. So we don't record the actual phone conversation, but we look at which phone number called which phone number at which time. But because this is an IP network, we look at which IP address connected to which IP address, over which port, what protocol, what time, how much data was transferred, etc. So the first thing that we do, we just turn this on in the network. It's supported in all major Cisco platforms, and the ones that's not supported, we're going to bring more support for NetFlow. It's a key priority for Cisco. This means that every single device in your network will start sending traffic, information about the traffic it sees, to a central collector. The first thing that we do, we start building this database. Every IP address that connects, we record every transaction they make, every connection they make, internal or external. But the problem is that NetFlow is just IP address based. So all you have is a massive database saying this IP address connected to this IP address, and this IP address to this IP address. It doesn't help us from a security perspective. So we need a little bit more. So we got the IP from NetFlow, and then we go out and ask the rest of the network, who is the user behind this IP address? Active Directory, ICE, Radius. Which application is being used? We can get that from a firewall. We can get it from a web proxy. Was this traffic NATed? Did it go through a firewall? Did it do network address translation? We can get that from a firewall. Was it permitted or denied? We get that from a firewall. So you have all this information about these IP addresses already in your network, so we just pull them in. Which means that going from this IP connected to this IP, instead it's Marcus Josefsson using Telnet from its Mac, sitting in building 4 on switch port number 11, in etc. Connecting to this particular server, running this particular software, using this application. Right? So now we have an itemized, very granular list of all IP to IP communication. I can search for devices, servers, users, applications. It becomes an interesting forensic database. Then we create the groups and do the machine learning. So we create groups of devices that should behave in a similar way. We take all our email servers, put them in one group, and baseline. What's normal behavior for email? What's normal behavior for wireless guests? What's normal behavior for a surveillance camera, an ATM machine, a door opener, whatever it is that you have? Over 1 week is the first baseline. It's a 3-month rolling baseline to understand what's normal per group. And then we start seeing alerts and alarms. This happens automatically. Just give us an IP range. We'll baseline that IP range and see what's normal behavior. And then when we see deviations against the normal, we will start sending out alerts. You can either get them through a SIM tool via syslog. You can look at it in the beautiful user interface. You can get an email sent to you. But more importantly, if you're using something like Cisco ICE, when you get that alert with that user, with that infected device, say my device over there, it's communicating to a botnet, it's scanning the network, it's downloading terabytes of data from the SQL servers. All of these things will trigger different alarms, and we say Marcus is hoarding data, he's scanning the network, he's connecting to a known bad on the outside. I want to get him off the network. Normally, that's a manual process. Here, once you get the alert, you can directly in the StealthWatch console click quarantine. A signal gets sent to ICE. ICE sends a signal to the switch, or the wireless LAN controller, or the VPN concentrator. And suddenly, we start using the network edge as an enforcement point, instead of using the network edge just for connectivity. So that means that we go from gathering data using the actual network devices, network as a sensor, to actually use the network as an enforcement point as well. So this is the overall kind of flow. We gather NetFlow, we collect it, and do some clever things with it. We add a lot of context. We analyze it to detect anomalies and threats. And then we're able to take that information, send it down to the network, and then quarantine a user, change a VLAN, change an access list based on the threats that we see. So let's take this into a security operations center. Let's take it to an everyday job that many of you guys do. This is a timeline of an incident. One of the perimeter devices, an anti-malware gateway, fires. It has detected that someone on the inside is connected to a, it's a virus, it's a worm, it's connected to a botnet, whatever it is. We see an indication of compromise. It's a malicious transaction. 7 minutes later, because these guys are very efficient, they manually disconnect this device. That is the whole timeline. Malicious transaction, detection, we disconnect the device. That's what we traditionally see with a perimeter defense approach. Right. So what is it that we're talking about here, and how could StealthWatch add to this? Someone on the outside connects to someone on the inside. Malicious traffic is detected. 7 minutes later, we disconnect this device. Simple, right? That's what we do for a living. We detect threats and we disconnect devices and remove the threats. But what we didn't see, because this was perimeter-only detection, we didn't see that this device that we removed 7 minutes later, during those 7 minutes, it aggressively scanned the network. It actually managed to successfully connect to other PCs and start sending data to them. If you look at a network behavior analysis, it's not normal behavior for a PC to connect to other PCs. It's not normal behavior for a PC to aggressively scan the network. So here we get two alarms that we attribute to this first PC. First, it's scanning the network, and it's touching other devices. Okay, and these devices have been touched. Then we see that these devices, in turn, are starting to aggressively scan and touch other devices. So the next algorithm will kick in and say, first, a device starts to scan. It sets up successful communication with a number of other devices. These devices, in turn, start to scan and touch others. What's that? That's a worm. So we've got a worm that's in our network. Just looking at network behavior and what's normal and what's not. So all these devices, they have scanning alarms, touching alarms, and then we also add worm alarms to them. Now, the next step in any attack is to get to somewhere that's interesting, something valuable. So in this case, the worm spreads, it infects a terminal server inside the data center, which is in the same subnet as one of the SQL servers. The terminal server starts to download gigs and terabytes of data from the SQL server in order to get it out of the organization. That's the next alarm that we see. It's not normal behavior for a terminal server to download gigs of SQL data. It's never happened before, and it's not normal behavior for the group terminal servers. Okay, so we get another alert here, just using behavior and machine learning. Data hoarding. Normal amount of data consumed from a terminal server is 50 meg a day. This particular one is downloading 50 gigs. Looking very strange. Then we see that the same terminal server, not only does it hoard a lot of data, download a lot of data, it also sends a lot of data out all of a sudden. That's not normal behavior either. It's never done that before. So we see gigs of data moving across the network from two nodes that have never done that before. So then we see a data exfiltration attempt. The last piece is actually trying to get the data out of the organization. So we moved it around to kind of cover our tracks, and then we do a DNS tunnel, an SSH tunnel, or an SSL tunnel just to get it out. Or maybe we can put it on Dropbox. So many options to get it out to encrypt the traffic. Again, the network will see this is not normal behavior. If you look at DNS tunneling, we can see the application inside this tunnel is peer-to-peer with FTP. It's not DNS. It's just using DNS ports. But we see the actual application is fake. Even if it's fully encrypted, DNS is not encrypted, so it's simple. But what if it's SSH? What if it's SSL? still we'll see it's not normal behavior for this device to upload gigs of data to the internet. So we have a data exfiltration alarm anyway, but with the DNS tunneling example, we can go deeper and say, you know what, this is a fake application. This is an application that's posing as DNS, but it's actually not. So let's go back to the timeline and see what do we get from StealthWatch. What does StealthWatch add? But before we do that, I forgot about this. Before we do that, let's think about all the other devices. This example, it involved secure devices, trusted users, authentication, network access control, antivirus, anti-malware clients. These devices should be secure. Many customers that I sit down with, and we do this very well, anomaly detection for these devices. Many customers I sit down with, the majority of the things that are connected, the clients in the network, are not PCs and Macs and servers anymore. It's surveillance cameras, it's robots, it's ATMs, it's printers, it's access card readers, it's POS terminals. That can sometimes be 70–80% of the connected clients. You can't put all these in Active Directory. You can't put agents on them. You can't run them through an IPS because it gets too expensive. Most of the time anyway. But the good thing is about IoT, the network behavior of these devices is almost 100% predictable. I go back to the surveillance camera. A compromised surveillance camera is so easy to detect because the behavior of a non-compromised surveillance camera is static. Send data from the client, which is the camera, to the server, certain port, protocol application, data volume, constant. Should always be going like that. As soon as it does something else, it's very easy for us to detect this. This is, in my opinion, the best chance we have for IoT protection. We can't try to install clients, and if we manage to authenticate the device, we'll do it with MAC addresses, which is not secure. Anyway, you can spoof a MAC address. Network behavior is, in my opinion, the best chance we have at doing IoT compromised devices detection, IoT security. But let's go back and look at the timeline again. So all the green stuff is stuff that it's additional information we get when we use the network as a sensor. We see the scanning of the network internally, just using switches. It never touched the perimeter. We see the successful connection and the spreading of malware laterally in the organization. We see the data hoarding from the SQL servers. We see the data exfiltration. And we see the fake application and the DNS tunneling in this case. So turning the network into a sensor, it's all about visibility, to seeing a lot more. So once you get that indication of compromise, you'll have a chance at every hop in the network where you have NetFlow, NBAR, and these kind of technologies to get a lot further and get a lot more visibility into what actually took place. These are some of the examples of algorithms that we have. We have 150. These are some of the classes of algorithms. Denial of service attacks, botnet detection, IoT security, worm propagation, data hoarding and data exfiltration. We've already talked about some of these, but we have around 150 of them, and we come up with new things all the time. So just to kind of summarize what we've been talking about, this is traditional network perimeter security. We inspect at perimeter, internet egress point. You turn NetFlow on, and you get all the devices you already have to start reporting on the traffic they see. The visibility that you get becomes something like this. We start to see every IP to IP communication. As soon as you connect to a switch or a wireless LAN controller or whatever it is, we start seeing all the traffic. You don't need to wait until it gets to the firewall. Then we get information about these great IP addresses that we see out there. Who is the user? What's the device type? What's the location? What application is being used? Is it NATed? Is it permitted or denied through a firewall? You have the information in your network, we just pull it in. And you get to somewhere like this from a visibility perspective, where you'll be able to say, I see all IP to IP communication. I have full context. and I can create policies of what should be allowed and what shouldn't. And then I have the machine learning that will automatically detect threats and automatically detect issues in my network using big data analytics. So before an attack happens, we make sure that the policies are in place, that there's no telnet flowing through your firewalls, they don't have rogue DNS or DHCP servers, that no one is using BitTorrent, for instance, that your surveillance cameras are only speaking to the surveillance camera servers, that your branches are only communicating to the data center, not to each other or to the internet, that all the users are actually going through the proxy, not directly to the internet. So we put the policy controls in to make sure that, okay, before an attack happens, we use this to make sure the policies are actually in place. There's no gaps. During an attack, we use the algorithms to detect breaches, different types of attacks. There's 150 algorithms. After an attack, we have a massive forensic database that don't stretch back days or minutes or hours. It can go back months or years. We have customers that save every IP to IP communication forever on a few terabytes of storage. So what do I need to do in order to enable this? This is what all networks look like. It's an access layer and distribution, a core. There's a number of branches. There's a data center. There's virtualized resources. There's a DMC. Just turn NetFlow on. Point the NetFlow to a collector. One thing that's important to point out is if you want to detect malicious traffic from this iPad going to the data center, you don't need to have NetFlow every step of the way. As long as we have NetFlow somewhere on this route, as long as one link in the chain from client to server gives us NetFlow, that's enough. So start turning it on in the data center, the internet egress point, the routers, maybe the DMC, and the core. You're going to get 95% visibility. Once you start to turn it on in the access layer, you're actually going to see this client connecting to this on the same physical switch on layer 2. We can do that as well. You can go in and look at VM to VM traffic with devices sitting on the same host. So two virtual machines living inside the same physical machine. They don't even touch the network. They communicate via the virtual switch. We can get the same level of visibility there on VMware today. On the roadmap, we also have the same for KVM and for Hyper-V. These are some of the platforms inside Cisco that support NetFlow. We're coming up with new stuff all the time. I'm Swedish. In Sweden, a lot of customers don't have 3K switches in the access layer. So the new 2K switches, 2960X, will have full NetFlow support. The UCS now have NetFlow support. We can get NetFlow. Sorry, I wasn't aware of Q&A. Anyone else? No? I'll be around afterwards as well, so please feel free to come up and ask questions. Thank you. Controllers and the firewalls. And again, you just need to catch it somewhere from the client to the server. One of the hops, the client, then the access, distribution, core, data center, etc. Right. So let's talk a little bit about threat detection, just to kind of visualize what I've been talking about. The configuration that you need to do is to give us IP ranges that make sense. So give me an IP range of a function. For instance, these are my email servers. I put them based on IP address in one group, and then I look at what's normal behavior for an email server. What's normal behavior for my SQL servers? What's normal behavior for my wireless guests, etc., etc. That's all you need to do. Just give us IP ranges. All IP addresses are normally sitting in at least two groups. So take, for instance, a surveillance camera. I like that example. Take a surveillance camera. It's in the functional group surveillance cameras. We compare it to all others. And it's in the location building 5. So we both baseline per location and we baseline per function. Once you see an individual in this group, we take the surveillance camera again because it's very simple. One of the surveillance cameras start to scan. That's not normal behavior. So the anomaly gets identified, and the algorithms will start working to identify exactly what is this. Is it a worm? Is it a reconnaissance attack? Is it a DDoS attack? Is it data exfiltration? And it will tell you in clear text, this surveillance camera is doing surveillance scanning. It's doing reconnaissance scanning of your network. Or it's part of a DDoS attack. Or strangely enough, this surveillance camera is downloading gigs of data from your SQL servers. That's not normal, right? So the first thing we do, we collect the flows. We look at around 90, 100 different attributes of the flow data, as you can see in point number 2. And then we create the baseline. The first baseline is a week. It's a rolling baseline of 3 months. And then we start to automatically detect deviations and threats. So analyze, collect the flows, look at the events that we identify, create alarms that make sense to us, and then push the alarms out to take an action. You can either look at an alarm table internally in the system to see ongoing alarms. You can zoom into an individual host. I'll show you that in the quick demo to see who had this, who is behind this, which is the user, what's the device type, what's the location. To look at the host where this threat comes from. You can get an email sent out. You can send an alert out via syslog to a SIEM tool or some other tool. Or again, you can use Cisco ICE as an example, or nowadays even third-party NAC, other NAC solutions to take an action and throw that device off the network, or quarantine them, or do PCAP, whatever it is that you want to do. Right. These are some examples of policies we talked about before an attack happens. You want to make sure that your network policies are enforced. Super simple to configure. FTP, for instance, if we detect any FTP traffic, give me an alert, and then we see the user, the device who originated this traffic. Telnet, BitTorrent, rogue servers, DHCP or DNS, for instance. Traffic between the military network and the internet. Traffic between the ATM and the ATM servers. Just simple examples. Here's a very simple one that we've done. Any of the internal IPs, internal groups, connecting to the external IP addresses, the external group. Don't look at any particular traffic unless it's BitTorrent. Then I want an alert. And here we see the number of violations. You click here, and you see who was the user, what was the device, when did it happen, how much data was transferred. This is from a live network in South Africa. The CIO implemented no BitTorrents. And every time he sees a BitTorrent user, he just throws them off the network. He doesn't even look who it is and what's going on. And he hasn't received a single complaint because people know they were doing something wrong, right? Using BitTorrent on a corporate network, clogging up the links. So this is very, very simple. It's very, very basic functionality, but it's so hard to get this somewhere else because we get it from all the network, not only traffic passing through that particular endpoint device, perimeter device, sorry. Right, let's talk a little bit about network performance monitoring. I'm just gonna quickly talk about the whole triage issue. Is it a network issue? Is it a server issue? Is it a security issue? Or is it an application issue? With NetFlow, you can get this information off the bat with one click. Someone calls and says, oh, the network is down. You can say, you know what, it's actually the WAN that's down. Or it's actually your device that seems to be communicating with a botnet, so it seems very compromised. Or it's that server has a 50,000 milliseconds response time, so the server is down, but the round trip time is kind of fine. So it's just a simple map that we created where you'll be able to see what's the server response time, what's the packet rate, what's the amount of, what's the traffic going on this link. And then you can see, is it a database problem? Is it an application problem? Or is it a web server problem? So it's a 3-tier application. Or is it actually the network that connects all the branches to the web front end, to the application, to the database? It's just one click, and you just use NetFlow to answer these questions. One of the key values for the network team is really around this when they start using StealthWatch. Security team uses for everything else I've spoken about, but for many networks team, this is gold dust because it saves a lot of time and energy. and a lot of politics potentially internally when people start pointing at each other when something goes wrong. IP doesn't lie. NetFlow doesn't lie. As soon as you connect, we see every single transaction you make, and we have measurements connected to those transactions to know exactly where you should be looking when there's an issue. Another example from the network team is we have an issue with performance between 10 and 11 every Wednesday. We don't really know what it is. Just use NetFlow and look at what's the top applications, what's the most active host on your network, top protocols. And you're quickly able to see, okay, it's actually the backup servers that's generating all this traffic that's clogging a few interfaces. So someone is running the backup in the AM instead of the PM. Typical thing we see in a POC. Instead of running around trying to do Wireshark and find out exactly what's going on, use NetFlow, and you'll be able to see these are the hosts that's generating all the traffic. They belong to the group backup servers. Call the application owner and say, can you just check what time you run your actual backups on the Wednesday? Oh, right, it's in the AM instead of the PM. Just when everyone else logs onto the network, you're running a massive backup job. Right, so that's network performance monitoring. Right, so let's talk a little bit about ICE and the ICE integration of StealthWatch. Like I mentioned, a good way to think about ICE is the security guard or the access control at the edge of a building. You want to go into the door, you need to provide credentials. You need to identify yourself, okay? We are kind of the surveillance camera that looks at once you enter the building, we're giving you access to see everything that you do. So NetFlow records everything and stores it in the NetFlow collector, every single thing that you do. The algorithms are kind of like the guy that watches the surveillance camera to detect what you're actually doing is harmful or not. And then sometimes it calls the security guard who provided you access and asks him to escort you off the building. Okay. I don't know if that analogy was good or bad. We'll see as we go through these slides. Right. So what we have here, this is typical network access control scenario. We have a user, his name is Joe. It's in Active Directory. It's got a secure device, which is also in Active Directory. So it identifies both as a user, it does user authentication, and it's also got a certificate for hardware. So it's doing both hardware and user identification. It connects via .1x to a switch, a radius lookup to ICE, ICE queries Active Directory, and we have a policy that says if you are a corporate user with a corporate device and you're in HR, these are the resources you should be able to access. An access list or a VLAN gets downloaded, and Joe goes ahead with his day. Then the access switches and all the way down to the data center, they all start to report into StealthWatch or cyber threat defense, call it what you like. And we detect that once we've let him in, it was authenticated with ICE, we have a policy, this is his VLAN, his access list. He aggressively scans the network. He's connecting to a botnet. We take the decision, we want to get him off. So we actually, in the actual interface, it's just one click, quarantine. And a signal gets sent from ICE down to the access switch. It's called change of authorization. And a new access list gets downloaded, or a new VLAN, or a new security group tag. And he gets lower access in the network. So this is kind of cool for a number of reasons. And one of them is, if he's infected, he's like, oh, I can't access the network. Someone shut me down. Then he goes from wired to wireless maybe. But he still needs to go to ICE, even if he changes IP address. We see the username of the device. He then might want to try to VPN. Again, same thing. ICE controls access. So once we have you in ICE as quarantined, you're quarantined everywhere, even if you change IP addresses and access methods. So you can run around as much as you want. And access is controlled directly at the edge. Once we have cleaned up this machine, we just click unquarantine, and a new access list gets downloaded. And he gets the full access that he had before. So the amount of manual intervention really decreases, but more importantly, we take the action at the edge instead of trying to block in a firewall or somewhere like that. So he loses all access to his peers. He can't spread and communicate, spread a worm, for instance. but I want to go back to IoT. It's kind of exactly the same use case, network behavior analysis, but we need to kind of think about these devices a lot more than we do. We talk too much, in my opinion, about servers and PCs and Macs, clients that we try to secure in other ways. But the IoT kind of devices, they are very vulnerable. They don't have advanced security built into them. We can't control them that much. We don't put agents on them. And a lot of the time, they make up 50% of the count inside a network. So it is very important to start thinking about IoT security in a slightly different way, because IoT is an enterprise issue. It's not manufacturing. A good example is the biggest bank I worked with when I worked in London. They had 40,000 clients that they knew about and 80,000 clients they didn't. Where do you even start, if you don't know the behavior of these clients? And we're seeing that with more and more customers. There's more devices that we don't exercise full control over than the devices that we do secure. So same thing here. We detect scanning activity, but instead we want to maybe do a PCAP of this traffic and do deep packet inspection, and then we can analyze the actual traffic instead of throwing it off the network. Okay. So I'll quickly kind of try to move on and speak a little bit about the architecture and then summarize before I do a very quick demo of the solution. So the full architecture looks something like this. You need to have infrastructure where you turn on flow. The flow gets sent to a collector, which stores all the information. All the IP to IP communication gets stored on a collector. That's a virtual machine or a physical sitting in the data center. The smallest one can handle around 10,000 users, 30,000 flows per second. The biggest one can do around 600,000 flows per second, which is around 200,000 users. And then we can cluster 10 of these together, so we can do 6 million flows. The biggest customers that we have is the Oracle, HPs, CIAs, the big customers out there. And they kind of run into, they want to push us even further. So we have countries or SPs who are trying to push millions of users through us, and we're kind of able to hold up. So we scale incredibly well up, but we also have a lot of customers with 100 or 200 or 300 users. So it scales as well down as it does up. So the collector stores all the data, does all the anomaly detection, and then we have a management console that is the reporting engine. We can also do PCAP. So we also have a packet capture device, which I, in the interest of time, haven't talked too much about. So once we detect an anomaly based on net flow, which is metadata, we can actually send a signal to the packet capture to start recording this and go back in time and get all the recording we had for this device, and then keep recording and do deep packet analytics on that as well. So you get the forensic sorts of deep packets as well as the metadata detection that we use. That's a box called a packet analyzer. Just a big storage array, really. It can take 10 gigs of continuous traffic for, I think it's 28 hours. So it's kind of a lot. If you have 10 gig continuous traffic, you can still save everything for 26 hours. So once you get an alert, someone is scanning, is doing botnets, is part of a DDoS attack, you go back and get as much previous raw packet capture involving this machine as possible, and you keep recording from the time that you saw the event. And that gives you the best of both worlds, best of the kind of deep packet capture, storage, intense, as well as the metadata, big data analytics using NetFlow. For devices that don't support NetFlow, we can actually spin traffic out to a flow sensor and create NetFlow and IPFix and send it to the collector. All customers have a flow sensor anyway, even if they have NetFlow everywhere, because it adds some additional fields that are interesting for us. URL information, application information, server response time, network response time. So you spin off the most important or relevant traffic to a flow sensor using tap or span. It adds some additional context to the flow data. It drops the payload, and send the additional context up to the collector. There's a virtual version of the flow sensor, and that helps out with VM to VM communication on the same host. So if we've got two virtual machines sitting on the same physical host, communicating inside the hypervisors using the virtual switch, it will never touch the network and you'll never get net flow unless you use Nexus 1000V instead of the B switch. But here you can actually drop in a flow sensor, and the flow sensor will tap into the virtual switch. You get exactly the same level of visibility on a VM to VM on the same host as you do for devices that are connected and going through parts of the network, access switches or data center switches or whatever it is that supports NetFlow. Here we see the context generators. We see the Active Directories, the web proxies, the ICE, those kind of devices. They just add context to the flow data. What's the username, device type, permit and deny, application, all these things. For traffic that's going to the outside world, we have a threat feed that identifies traffic going to known botnets, bogon IP addresses, or Tor networks. So if you have internal communication from your internal IP space to the external that's going to one of these bad places, you get an alert on that as well, all based on the flow data. So just to kind of summarize before I do a quick demo, the key function and functionality is going from 30-40% visibility to 100. Use your switches, your routers, your wireless LAN controllers. That's the big investment you've already done. You invested in a good network. Use it to gain visibility from a security and network performance perspective as well. Get a lot closer to one-to-one visibility, every IP to IP communication. Before an attack happens, we make sure that the policies are actually in place. There's no telnet, no DHCP servers, no remote access flowing through the firewall, whatever policies we have in place. During an attack, we let the algorithms do the jobs. They will detect three major things: attackers, devices on the in or outside doing bad things based on network behavior. We'll not only see the attackers, we'll see the targets as well. So not only who is doing bad things, but which devices are having bad things done to them. Who's being DDoSed, for instance? Who's being scanned? Who's being touched? So first we have an index tracking the main villains, and then we have another one tracking the main targets. The third one is tracking devices that are moving data around in a suspicious way. Like the terminal server, for instance. Not normal to download gigs of data of SQL and then sending it to a host in the client host group. An example of suspicious data hoarding. Or data exfiltration, not normal using DNS, a fake application to pump out gigs of data via normal clients in the network. So those are the three indexes that we track for every single IP address that's on your network, on the client or the server side. We then add context from ICE, from Active Directory, from web proxies, from firewalls, whatever the devices are that you have, to get more information about the username, the device type, all these things that we need to do a good security incident analysis. And after the fact, once we've seen an indication of compromise, once we have a worm on a network, we can use this for forensic data and go back months and years and days, not only minutes in point of time. Because all NetFlow data is stored in one single place, and even with a massive organization with Cisco with hundreds of thousands of endpoints, we store every IP to IP communication internally and externally for 90 days on a few terabytes. So we do some clever things to do good data retention. Right, so let me just finish off with like a quick 5-minute demo, and I'll go back to one of my favorite examples, Edward Snowden. How do we protect ourselves against someone like Edward? He's a trusted user. He's, analyst for the NSA. with a trusted device that has all the security stuff that NSA has bought over time installed on it, how do we protect ourselves against him? The malicious insider, we trust him. His device is secure. How are we going to detect that Edward is going to steal the whole database and then walk off and give it to WikiLeaks? So let's take that example. So Edward, he connects to a terminal server, same example as I've been using for simplicity's sake. The terminal server, he wants to cover his tracks. He don't want to connect directly to the servers where the data is held. He gets the terminal server to download the data, and then he uses the terminal server to upload the data. He just connects to it, so he's just logged on. So let's see what this looks like from a GUI perspective. This is the first thing that you will see when you open up the new console. This is ongoing threats right now, and these are the different classes of threats. So we see high concern index, devices that are being attacked. We see reconnaissance. We see devices that are currently infected by botnets, so command and control servers, DDoS, and here we have a data hoarding and a data exfiltration alarm that are currently ongoing. These are some of the alarms by type. Again, we have 120 different algorithms that will generate different types of alarms. This is the alarms that we've seen today. This is the top applications in the network, and this is just network traffic. But okay, we see we've got two things going on. So we click on the host, so because we want to see the ongoing, see which hosts have alarms attributed to them. So the first thing we see, these are the alarms, concern index. We have DDoS source, DDoS targets, etc., things that I spoke about before. But here we see data hoarding, devices hoarding data, stealing data, downloading lots of data. And we see that we have two devices here with very high indexes. Everything below 100% is considered normal because that's the baseline we set for the group. But when you have a device that has 1.2 million compared to 100%, then that's an anomaly that we need to probably investigate. And we see that the database servers has got 1.2 million percent of concern index, and we see that the terminal server has 75,000% of concern. So just based on network behavior, what amount of data do these devices normally move around, and where do they move it? So that's the index and the severity. We see the host name and the host group. And in this case, we want to look closer at the terminal server. So we click on this IP address here of the terminal server, who is in the terminal server function group in the data center location. So we click here on this host. Here is information about this host. We see it's currently active on the network. We see that Edward Snowden is logged onto it. We see the MAC address. We see the vendor of that MAC address. It belongs to Dell. It's a Dell manufactured PC, it looks like. And the device type is a Windows 7 workstation. This information we pull in from ICE. So we don't need to generate this ourselves. ICE has this information, or Active Directory has some of it. We just pull it in, right? We see the ongoing alarms for this particular host. We see the alarms by type over the last 7 days. And then we look at the traffic. This is this host. This is the terminal server. This is the traffic internally. This is traffic externally from this host. There's a thick line going to the database servers, and there's a thick line going to Puerto Rico on the outside. And then we can look down here to see the actual internal traffic. So we see, okay, there's 34 gigs of data. It's SQL. That should be that one going to the database servers. But let's look at the external traffic as well. Traffic going here, so we click on this tab here to see external traffic. And we see that 3 gigs of data has recently been uploaded via peer-to-peer to Puerto Rico. So then we decide we want to run a super quick query on this data to see what was going from this device to Puerto Rico. And we see, okay, over the last few minutes, we see it's 12:54 to 12:57. That's the last 3 minutes. We've had 300 megs over port 53. What's that? It's DNS. But the actual application, it looks like a peer-to-peer. It's going to Puerto Rico. So that was a very, very short demo of how you go from just detecting a behavior anomaly to zoom into a host that is doing this strange behavior and do a quick analysis and say, okay, a lot of downloading from the SQL databases, that generated an alarm, and we see a lot of traffic going out, and we see where it goes to. We can do a lookup of that host in Puerto Rico. We see which the application that's being used. We see which ports. And in this case, it's very simple for us to detect. We have a DNS tunneling event going on, and we have 300 megs have left the organization in the last 3 minutes. So that is just a very, very quick demo. So with all that being said, I've run over, I think, 1 or 2 minutes, but not much more. So I just want to thank you.